video on planes in 3 space. So by planes, we don't mean airplanes, though those are very fun as well, but by plane we just mean the two-dimensional flat surface, right? So flat surface, and in 3 space, that just refers to in 3 dimensions or in space, 3 space. Okay, so let's say we're going to start off by saying that we have a point P naught, okay? P naught is the following. It has coordinates x naught, y naught, and z naught, okay? The naught is the little o at the, or 0 or o at the bottom there. Okay, so let's say we have this point and it lives in a plane, okay? So I'm going to draw a little plane here, okay? So here's our plane, and here's P naught, all right? So there's P naught, and it has those coordinates x naught, y naught, z naught. So once we have this, then it only follows that I should introduce the normal vector to the plane. So normal vector would look something like this, okay? So this, I'll call it n for normal. And the normal vector, and we'll say that it has directions a, b, c, because it's a vector, right? So it has to have the arrow brackets here. And this normal vector, anything, whenever you see the word normal, you're going to think that it is perpendicular to something. And in this case, the normal vector is perpendicular to the plane, okay? So this normal vector is perpendicular to, and I'll call it fancy P, the plane P, okay? So this is the plane there, P. All right, so from this, we can conclude that, let's say we have a random point Q, okay? And we say that Q, which could have any coordinates x, y, z, okay, and that's not an arrow bracket, hold on here. Okay, any point Q can lie on the plane, x, y, z, lies on the plane P if, and this is a big if P naught Q, if the vector formed going from P naught to Q, let's say Q's over here, so here's Q, x, y, z, if the vector pointing like that from P naught to Q is perpendicular to n, our normal vector. So that means that if we form a vector from P naught to Q and it happens to be perpendicular, if it makes a right angle with the normal vector, that means Q has to lie on the plane P, the fancy P, okay? So likewise, we could have Q being over here or something. Let's say Q's over here. And if we draw that vector from P naught to Q and it does make this right angle, sorry, it's in the back here, but there's a right angle back there, then Q also has to lie on the plane because it's perpendicular to n, our normal vector. And every vector on the plane must be perpendicular to that normal vector. Okay? So, mathematically, the way you look at this is if P naught Q is perpendicular to n, then that means that the dot product between the two, so n dot P naught Q, must equal 0, right? We've learned this in the dot product section. Okay, so component-wise, this is how you would write it out, is A, B, C, and then dotted with P naught Q to solve for the components of a vector, given its 2 points, right? Here's our first point, here's our end point. We take the end point components, right, and we subtract off the start point components. So it'll look like this. And lastly, Z minus Z naught. Okay? So all of this has to equal 0. The dot product has to equal 0, right? And then I'll continue down here and we'll solve for the dot product. So A times the first component of P naught Q, so that's x minus x naught. Then we're going to add B times y minus y naught plus C times Z minus Z naught, okay? Equals 0. All right, and everything that I've written up to this point, so starting from here, starting from this equation, sorry, I'll use a different symbol. Not a star, but a check mark. So starting from here, this check mark, up to here, these are all valid equations for a plane, okay? So equations for a plane in 3 dimensions, okay? And I'll continue on the next slide. So if we distribute the A, B, and C in respectively, we get AX minus AX naught plus by minus by naught plus cz minus cz naught equals 0. Okay? And at this point, we can just simply add these ones to the right side, to both sides actually. Add them over to move them to the right side and make them positive. Okay? We're going to do the same thing over here. So plus ax naught plus by naught plus cz naught. Got some problems with the screen there. Okay, there we go. And these cancel out on the left side, and we're left with ax plus by plus cz is equal to ax naught plus by naught plus cz naught. Okay, so at this point, here we have another equation for a plane, and this you can see is a, b, c on the left side dotted with x, y, z, right? So this is like a, b, c dotted with x, y, z. A lot of this is just another, just kind of seeing the different ways you can write things and like move everything around and kind of play with what we have. So this is another way to write it. And then on the right side, that would be a way of saying a, b, c dotted with x naught, y naught, and z naught. And in this sense, then we have our normal vector dotted with, and x, y, z was the OQ point. Okay, so that was the point we were concerned with. And then this is n, our normal vector, dotted with O P naught, right? So this is our P naught point. So anyways, the point of this is saying that this, again, is another way to write an equation of a plane. And going from this line here, sorry, there's so many lines going on, but from this line here that I'm putting brackets around, this could also turn into ax plus by plus cz, so the left stays the same, and sometimes this whole entire right side, since these are just constants, they're all numbers, right? X, y, and z are variables, but like this x, this y, this z, they're all variables, but the x naught, y naught, z naught, those belong to the point P naught, which we defined in the beginning. We know that's on the plane, okay? So this often is referred to as just a single letter D, okay? That just subs in for all of the stuff circled above, okay? So, yeah, so this is, again, we've come to another, like, I guess this is the most common form of an equation for a plane, which is n, our normal vector, dotted with x, y, z, that's a random point, right, equals d, okay? Also known as ax plus by plus cz is equal to d, where now we know from the derivation that d equals a times x naught plus b times y naught plus c times z naught, okay? So this is a very common way to write the equation of the plane. Okay, so let's do an example of this since we've just been working with some letters and things here and there, which might be a little bit confusing. So what we're going to do is find the equation. So we're going to find equation of the plane through, and I'll give you a point here, through P naught, which is defined as 2, 0, 1, with the normal vector being the following, 5, -2, and 3. Okay, so this is like our A, B, C, and this is like our x naught, y naught, z naught, okay? So I'm going to use the last definition that I gave you for the equation of the plane, and this is n dot x, y, z is equal to d, all right? And remember, d is equal to well, I'll write it like this. So d is the same thing as n dot OP naught, okay? And that is A, B, C dotted with our point P, but just written as a vector. Okay, so 2, 0, 1 with arrow brackets. Okay, so now what we can do is basically just solve for the right side. And then on the left side, we just have n is ABC, so we see ABC twice, right? Our direction vector for the normal vector. Dotted with x, y, z, and in our equation, we're just going to have our variables, these things, these guys, left as variables. So that's just going to be x, y, z in the end. So anyways, so what we can do now is just plug in our given ABC, right? Our normal vector here, and we'll solve for the right side and then kind of just simplify the left side. So the left side's going to look like 5, -2, and 3 when we actually substitute in numbers for ABC, dotted with X, Y, and Z, okay? And then on the right side for ABC, we're going to sub in the same things, 5, -2, 3, dotted with 2, 0, 1, which is the vector form of our point, right? Our given point that is definitely on the plane. Okay, and then this right side, again, this is just D, commonly thought of as D. Okay, it's just a constant, and we'll calculate this. So on the right side, we're going to have 5 times 2. So 5 times 2 is 10, plus -2 times 0, 0, plus a 3 times 1, and so that's just a 3. And then on the left side, we're going to have 5 times x, so just 5x, and then plus a -2 times y, -2 times y, plus a 3z, okay? Okay, so the final step is just to make things look a little bit nicer. So we have a 5x minus 2y plus 3z is equal to 13, okay? So this is our final equation of the plane, given that it goes through this point and it has this normal vector.